Go for it, Jeff.
What?
Go for it.
Well, it's a little bit flickery.
Ah,
This is the one I really want.
nice. You're socially isolating.
Yeah, it's socially isolating.
Go for it, Jeff.
What?
Go for it.
Well, it's a little bit flickery.
Ah,
This is the one I really want.
I'm sending you the link
Nice.
to the YouTube
You're
live if you
socially
want to
isolated.
send it.
Yeah, it's socially isolating.
go for it, Jeff. Go for it.
Well, it's a little
Okay.
bit flickery. Well, it's a little bit flickery. This is the one I really want.
I'm sending you the link to the YouTube
You're
live if
socially
you want to
isolated.
send it.
Ah,
So-
nice.
Hello everybody, how are you?
Good.
Hi, Nico. Good.
Hi.
Hello.
So welcome to this this streaming celebrating 1 year of the black hole image, this breakthrough from the HT collaboration, and we are streaming from the ALMA account. Everybody's at home now during due to the current situation of COVID-19. So I'm very happy to introduce. I have with us we have Alejandro Saez, engineering. Please say hello.
Hello.
From ALMA, he's leading from the ALMA correlator and very active participation in the HT and the LBI observations. Jeff Crew from MIT Haystack Observatory.
Hi.
Hi, Jeff. So he has been coming to ALMA for the past maybe 7 years, I don't know, maybe more.
Maybe more, yeah.
Maybe more. Helping us to have the observatory ready to do these VLBI observations. Violet Pellizzeri, she's from Italy, astronomer. She has been our lead astronomer in the VLBI observation in the ALMA group. Hi, Violet.
Hi, Nico. Hi, everyone.
So then I'm saying the names in the order I see you, Dilay, so don't take it personal. Then I have Hugo. He has been helping Violet all the way around with the EHT observations, and well, maybe you can tell what you're gonna do afterwards, because he just joined ALMA with a new position also in the last few weeks. And last but not least, Ciriaco, who is an Italian also astronomer coming with Jeff, helping us to get the observation runs for VLBI every year. Not this year, unfortunately. So we're all very happy to be here with you and having you celebrate with us in this special way, a special party, online party to celebrate all this. I prepared a little presentation to remember what was last year breakthrough event. I'm going to share with you, make a little introduction, and then we can open for questions and the conversation. I don't know if somebody of the team wants to say something else while I share this. Okay, so do you see the presentation?
Yes, we do.
Yes.
Yes.
Okay.
Yes.
Before I start, if anybody from the audience has questions, you can please put it on the comments on YouTube, or if you're in the Zoom webinar, you can ask them from the Q&A tool or the Zoom chat tool. Okay, where is, if I do this? Okay, so we're 1 year later after the HT black hole. This one an event, as you can see in this picture, a very happy event. We had Jeff on the room, Alejandro, Violet with a green dress, Hugo with her behind her, and the rest of the team were Sean, between Alejandro and Violet, is the ALMA director. Javier is the ESO director. and a bunch of people very happy. This was the setup for the press conference, and it was a press conference made simultaneously in 5 cities around the world, in Taiwan, in Tokyo, in Washington, in the United States, and in Brussels, in the European Commission. So at the same time, we were streaming from all the other 4 places, and of course in Santiago from the from the ALMA headquarters. So it was about the ST observations, who made this image using 8 radio telescopes around the world to form a big telescope. All the details, technical details, will explain the technical people with us here today. To deliver this now iconic image we all have seen, I'm just making a little remembering of all this so everybody can freshen up a little. We're gonna come back to this image whenever you need them, guys, so if you need to explain things afterwards. The result of this image were 6 papers in the Astrophysical Journal Letters, published just a year ago on April 10. Here you can see Chiriaco, Violet, Jeff, everybody working, Alejandro at the ALMA to make the observations. Here you can see other parts of the team all around the world working from the same purpose, in the South Pole Telescope, in Pico Veleta, in APEX, and it was chose the Breakthrough Science Discovery of the Year by Science Magazine by the end of 2019, for example. The room was plenty of journalists, plenty of VIPs. We had the Chilean Science Minister of Science, the Chilean Science Minister, sorry. Wow, and this was, the result of this was we were on the front page of most of the newspapers around the world. There was a Google Doodle made for. We even were used for humor against Brexit or about Brexit. YouTube influencer Javier Santolaya made a special delivery. We have memes with cats, memes with billboards, memes by Lego. The estimated global audience was 4.5 billion people around the world, not simultaneously a year ago, but on the coming weeks, everybody, 4.5 billion people were estimated knew about this breakthrough discovery. And I just don't want to leave behind all the people that support the work here in Chile that weren't part of the news, but supported all the work the good work we made for delivering this press conference. So these were all the people behind the scenes working in the Chilean part, in the Santiago event. So more memes, just so you can remember all these ones, M87, Homer eating the donuts, whatever. And it was a very happy moment at the end. So I just put this to finish the presentation. So I'm gonna leave you with Violet now. I don't know, Violet, if you want, I leave you with the image, so you can actually tell us a little more about how you feel about the image now, a year later, and how and what you can take, what you take with you from this experience.
Yeah, thank you for having us revisit briefly this moment last year. I must admit that watching these images again, I'm going through a bit the emotion that we went through a year ago exactly, and I've forgotten how nervous I was, and I think all of us were probably. There was a lot of adrenaline and a lot of anxiety, expectations about we had to be showing the image at exactly the same time in all sides of the world, so they were also sort of, trying to keep up the momentum, trying to keep, look on the watch, and all of this is coming back, just watching, going through your slides. But it's a very happy memory. It was an amazing journey for us, since we only started the observations just a few years before. In fact, I remember that when we took these images, here I'm visited by my current boss. My current boss is he's asking me why I have stars on my shirt. Come enjoy it. Really? No, okay, that was good. So yeah, my life is very different a year later. As you can see, all of our lives are very different a year later. So new situations. Yes, so I remember when we took the first images were the telescope, and we said, I think this was Chiriaco actually writing some journalists saying, we're taking the picture of the century at ALMA, right? All of us were at ALMA taking those images that were shown last year. I remember him saying, we're taking the picture of the century, and I thought, oh, it's being very optimistic. So we actually, it was the moment we were taking those images, and so it's even more amazing, thinking how well we did. But I'd like to give the word to the others and see what their thoughts were about the presentation.
Jeff, maybe you can continue.
Yeah, I was just thinking, it's a lot changes in a year, and I know that I've actually spent a lot of time over the last year working not just with that image, but there's other data that we took that is actually filling my time. And the thought I was having was here we are again with the entire global village sharing a different kind of moment. We all are working at home and hoping to get through as well as we can. But we can keep our spirits up. I think we'll all get through this together, and it feels good to be part of a global community sharing things, good and bad.
Nice. Just to finish, let's continue with Alejandro to continue with this first round of thoughts about what you feel a year later, please.
Oh, well, it is still amazing to see that image, even if it was repeated over and over. I'm still amazing every time when I see that image. But for me, it gives me a special taste because it's been more than 10 years working for this project. So at the end, after a long journey, see that image, it's a really great experience. I have a really nice feelings about what was the outcome of that work. So it really still gives me good memories to me.
Excellent. Chiriaco, please join us.
Yes, so as Alejandro, also for me is the same, because I've been working on this project for many years, since 2014. And actually I was dreaming already about this project well before I joined. And I remember, writing scientific reports, reviewing the science that we could do, and saying things like, with this project, we will demonstrate that black holes are not just a mathematical abstraction, a solution to an equation, is not science fiction. We will actually see it. And, I was writing those sentences, but one part of me was not really believing it. So what I think it has changed after the publication of the image is that now we have some kind of experience with our senses that the black holes actually exist. And obviously, the ultimate goal is, to test that at the final frontier of a black hole, close to an event horizon, the theory, Einstein theory of general relativity, still correctly describes gravity, and that's the thing, the motivation that keeps us going.
Super, Hugo.
So yeah, I'm the newbie among everyone, but yeah, I just want to say a shout out to also Ruben Herrero, who was also in those observations here from ALMA, and he's in Europe. So I hope he's fine as well. But yeah, I mean, we were the newbies, and every time we got more involved with the whole experience was amazing, and getting to know the system and the project more and more with these guys that you see. It was a really nice experience. Learning curve, just top notch. So yeah, and then it's all about how the community reacted. I mean, I'm one of those that thought that the whole thing would last for 2 days, 1 day or so, like the traditional thing, and then it's still going. And we are celebrating 1 year of this revolutionary image. And hopefully more will come, depending on what the community will do in the future. But this image on my back is actually, I hope you can see it properly. It's actually from XKCD on top, overlaying on top of the ring. You can put solar system to scale, and it's amazing, even for an astronomer that has been working on it for a few years and 10 years. And when we see this image, it does amaze us and puts us everything into perspective. And as the others said, I mean, it's just mind-blowing and very worth very worth the time that you spend on this one. So it's rewarding, I will say. Yeah, it's a very cool experience.
Excellent, excellent. So I'm gonna reshare the presentation, but just to put the image and ask Jeff maybe if he can re-explain us a little. I remember that last year it was Jeff who explained us what we were seeing, and it was a very nice explanation. I think we can refresh a little our memories now. If you can explain us what we're seeing now.
Sure. So as everyone knows, gravity holds us to the earth and it pulls us. And we in our daily lives can't ignore gravity. And if you're in the vicinity of a black hole, well, the gravity is a lot stronger, but in many ways it's the same thing. Planets go around our sun, satellites go around the earth, and the gravity of a black hole is strong enough that light can get bent by it and even go in orbit around the black hole. So most of what we're seeing here is a bright ring, which is coming from the region of space where light is actually in orbit around the black hole. The extremely fun part of this is that the gravity is so strong and light is bent that light actually comes. So in this view that Nico has shown us, we're off at the right looking at the black hole, and all those white lines are ray paths which go from the vicinity of the black hole to us. And you can see a bright horizontal line above the black hole and a bright horizontal line below the black hole. The black hole's at the center of the image. And that's basically bringing forward the fact that the most, if you look at the many places light can come from, it's dominantly coming from those particular areas, which is why the black hole looks like a ring, and that's most of what we see. The really cool part is, whoops, no, go back, Nico.
Okay,
In those other paths, you can see some paths going straight up where we are actually seeing light that came from 90 degrees away from something off to the top or even something off to the bottom. Light from those areas also gets pulled by the black hole and shot towards us. So in fact, what we see in this ring is all the light from everything around the black hole, not just the ring, but all the material, the accretion disk, the jet, all of it feeds into the image that we see. And very much like funhouse mirrors, what you get isn't what you think you should be seeing, and untangling all of that is actually extremely difficult. And we address some of that in our later papers, but indeed, that's where most of the excitement is now, is trying to understand how to disentangle all the light that we see and learn something about this object.
And if we see this image, can you help
So-
us a little?
Yeah, so in this image, you know, your eye can pick out Homer's donut, and you can measure its diameter on the sky. And, you know, as I've indicated there, we measured it at about 43 micro arc seconds. An arc second is one of those units that astronomers have used for centuries. Um, a circle has 360 degrees in it. Each degree has 60 has 60 arc minutes, and every arc minute has an arc second. And then if you have 1,000,000 of those, well, you have a micro arc second. So it's a really tiny angle on the sky, but we were able to measure it because we can see this image. And Einstein's algebra basically tells us if you know how big that region is, then you know how much the black hole weighs. And one of the exciting things was that this particular size very nearly matched up one of the measurements for the mass of this object based on other measurements that astronomers can make. So it's not only did we see something, not only do we get a number, but the number is consistent with what people had independently measured. So as I say, that measurement is going to, you know, basically in orbit. Light is in orbit around it, but as I say, it's not so much that light is in orbit, because the light that's in orbit we don't get to see, but that also light that goes near those orbits is what we get to see.
Excellent, excellent, very nice. Oh, sorry, I didn't want to do that. So, and Chiriaco, I saw this Tuesday. We released new data from the EHT from other objects. I don't know if you are the right person to comment a little on it, or maybe Violet or Jeff. I don't know.
The new object, the results on 3C279.
Yeah.
Okay, sure, I can comment on that.
Excellent. Yeah, I'll share it. I'll share on the screen.
Yeah, maybe you can share the picture. In the meantime, I can remind people that in addition to our key two science targets, M87 that we already published the image, and Sagittarius, the center of our own galaxy. With EHT, actually, we are observing a small sample of black holes in so-called active galactic nuclei, or AGNs, which are in distant galaxies. And one of these objects is the quasar 3C279. And a quasar is the contraction of quasi-stellar. We astronomers have very wild fantasy when it comes to nomenclature and giving names to things. And the reason why we called it a quasar or quasi-stellar is because it looks like an ultra bright point of light. As seen from Earth, it looks like a star, except that is billions of light years away from us. So it's even much farther away than M87. And therefore, if it were a star, we could not see it. Instead, it has a huge amount of energy, it's a huge source of energy. And this happens when you have huge quantity of gas, also in the form of stars, that fall into a giant black hole. In the case of 3C279, the mass is about 1 billion times the mass of our sun. I must say that the mass doesn't fall directly onto the black hole. This never happens in nature. Instead, it's settled in a very large disk of glowing plasma. So a plasma that is heated to temperatures of billions of degrees. And we call this an accretion disk because this is from where the supermassive black hole actually accretes the mass. So the black hole is feeding on this accretion disk. And the interesting part is the part of this material in the disk is actually expelled into jets of relativistic particles, which means that this material, particles like electrons, which are moving at speeds close to the speed of light. A little bit like happens in M87. And with these new observations, we don't have obviously the resolution, the resolving power to see the shadow of the black hole, because again, these objects are very distant. 3C279 is about 5 billion years, billion light years away. So it's super far, but with EHT, we can observe the resolving power of 1 light day. So it's a huge resolving power. So for the first time, we can really peer into the central region, and what we managed to see, you're seeing now in the video, images at increasing angular resolution. We managed to see details of the jet, of the base of the jet that was not possible before. In particular, we see that the jet is not straight at the base. It's kind of a curve, has a curved shape. And not only that, most importantly, as you see, there are two components. And one of these components is almost perpendicular to the jet. And in principle, this could be coming from the accretion disk, from which these jets that propagate for thousands and millions of light years across the galaxy and outside are expelled. So in brief, for the first time, we are seeing what is inside the base of these gigantic jets, and better understand the physical process related to their formation and acceleration and collimation mechanism, which is a topic that has been open for 50 years in modern astrophysics.
And it doesn't have anything to do with the fact that the black hole of M87 looked like a 0, and a year after you just release an image that looks like a 1?
I didn't get the question.
No,
sorry.
it's a joke. So it's a joke.
I think we are publishing a picture that
So
looks completely different.
Next year, we'll
Next
be
year, are we having a black hole in the shape of a 2?
Yeah, we get a
we are building some kind of book, photographic book. So we don't want all black holes to look like each other, right? We want to have some variety. Sorry, I didn't your joke initially.
No, don't worry. No, just you were talking about the relativistic jet. I don't know if you or somebody else can answer me that, but I read in the release that some of the particles there look like they are going faster than light, but it's just apparently
superluminal motion.
An illusion.
Yeah, it's this is a general thing about jets. When they are emitted, they travel, so the electrons would travel from the black hole. If you look here at the center, the stuff at the top is probably where the black hole is sitting. And then to the bottom, going down, it's the jet. So this jet moves over time. At the beginning, when this jet started being studied in the 80s, they noticed that some of these particles were moving at a speed that was faster than the speed of light. Somebody's typing. Sorry, is that Jeff? Caught you. Thank you. So they looked like they were typing. They were actually moving faster than the speed of light, which was amazing. People are like, "Oh my God, this is it's a new. Maybe the speed of light is not the maximum we can achieve. We can actually go faster." So they thought they were onto new physics, a new phenomenon. But then so this was termed superluminal motion. It's the motion which jets travel faster. But it turned out to be just a geometric effect. So, it's a little disappointing in terms of new physics, but it's actually better because it's now understood. So the jet, instead of being perpendicular to our line of sight, is actually moving towards our line of sight. So distance was more than you would have, calculated if it was perpendicular. So it was all just, looked like, but it wasn't faster. And this is true for most jets that we now observe. This is well understood. In fact, you can use that to calculate the angle the jet has with respect to us.
Nice. So that's the explanation why it looks like it goes faster, but it doesn't go faster. Okay, so I want Alejandro, if you can tell us a little more about the technical challenge of getting ALMA able to observe these kind of images, like the black hole last year or Quasar 3C279 this year.
Well, first of all, as Jeff said before, for making this image, it's quite important to achieve an angular resolution so fine. It means that we have the ability, we should have the ability to observe a really small object, okay? But in order to accomplish that, we really need to have a really large telescope, okay? But it's really impossible or hard to make a really large telescope, even in this case when we are talking about a telescope that should be the size of the Earth, okay? So the trick is to use several telescopes and make them work together at the same pace. And that was one of the biggest challenge for this kind of observation. In the particular case of ALMA, we are talking about a telescope that at that time was under construction. So asking for adding a new feature to the telescope was something really crazy. But well, fortunately, the team was able to manage the project in order to get fit into the ALMA telescope. And it was challenging, but it was obviously doable because thanks to the people who originally designed the correlator, we already had the hooks for connecting the needed hardware for accomplish this kind of observation. I mean, we had the hooks for connecting a recorder and get all the data for then later processing at the Haystack Observatory. That's all. Did I miss something?
Yes, but how did you, so I understand you had to install a new maser, no? To be able to...
Oh, yes, that's right. As I said before, since we have several telescopes working at the same time, in some way we have to ensure that everybody is working at the same frequency, and they are working at the same pace, okay? So if you, for example, if we put an example, your own watch, you can see that along the time there will be a drift in time respect to another watch. I mean, maybe 1 second or something like that. But this is something that is not acceptable for accomplish this kind of observation. So we really have to ensure to have a really, really precise synchronization among the different telescopes. So the way to achieve that goal was using a really, really stable clock generation based on a H-maser, okay? And each single telescope that was part of this endeavor was equipped with that kind of clock. So this was another challenge for making this happen.
Sorry. And this maser, it's still useful for other observation, or it used only for HT observation?
Well, in the case of ALMA, for regular observation where no other telescope are needed, we don't really need to use this telescope, but we are actually using it. Excuse me, this maser. But if we want to observe with other telescope, we really have to use it.
Okay, so we use it, but we could not use it.
Exactly, because before I start with this project, ALMA was equipped with another clock, which was, let's say, less stable than this one. And ALMA was able to produce the science for what was designed. But in this case, since we have to keep a really good synchronization among all other telescopes, we had to update the clock of the telescope for this one, which is really stable.
Excellent, excellent.
If I may just add a comment, I think this is one of the things that's nice working for ALMA in collaboration with the EHT has actually been that the maser was bought by the EHT and installed with the help of the EHT team. So they also contributed to ALMA this way. Like you said, it should be used for the EHT observations, but we're now using it for all our observations, which is obviously an improvement. So
excellent, excellent. So
yes.
Hugo, you just arrived again to ALMA a few weeks earlier. And are you going to have some EHT and VLBI role in your new position?
So yeah, I'm back. I was here 3 years as a fellow. It's basically a 3-year postdoctorate program. And after those 3 years, I got reassigned to a new position. And one of the duties, yes, it's to keep coordinating and preparing the observations together with Violette and 2 other fellows here at ALMA. So it's Marilou Janton and David Rebolledo, pardon. So it's always a team, either in all the stations that may shape EHT. So yeah, and now I'm included in that team again, and it's again, it's learning curve still grows. I'm still learning from all the systems, and hopefully I'll be able to help more and more beyond what I've done already. So
excellent. And so what's coming? I don't know who wants to take this one, but what is coming in the near future for EHT and VLBI observations?
So I'll take part of that question, but people will probably complement. So ALMA, it's also part of or contributes also to another array, which is the global millimeter VLBI array. So it's 2 types of arrays, and they both kind of complement each other. EHT is all about the detail of the central cores of these galaxies, while GMVA can explore a little bit outwards, and also what we were talking about, the jet formation physics that Chiriaco was telling about as well. As you can see, it starts in my, I don't know if you can see my image, but don't worry. So in the ring that you can actually see, it's basically dominated by the core, but also it's hard to tell from that image how's the formation of the jet going, basically. So we still are not sure whether the image that we see is actually also comprises some emission from the jet of M87. So basically it's all about complementing that view, and GMVA can help as well. So, and beyond M87, beyond SET-GA, now you've seen the result from 3C279, ALMA and all these stations together will try to actually start observing fainter and fainter galaxies. So what it means is the goal of this is actually to improve the statistics, because basically trying to confirm a theory or set a path in research based on just one observation is definitely a no-go. So you need more, and one of the future capabilities from ALMA, and allows also to extend this to the EHTC and also GMVA, is actually observe fainter and fainter supermassive black holes, and also eventually the gas around them. So it's still a lot to do. There's still a lot to do. I don't know if anyone can complement this.
Chiriaco?
I can perhaps add how the EHT is going to grow in the future years, beside the science that I will be tackling. Some people that are listening might not know that since 2017, where we had 8 telescopes observing from 6 sites, as you showed at the beginning, we have added more telescopes. So since actually 2018, so the year after, we added a telescope in Greenland. So we are covering the northern sources. So from the North Pole is much easier and much better to image the sources that are a little bit northern, like M87. And this year, we were supposed to observe adding an additional telescope in Arizona. So there is already a telescope in Arizona. We will add another one, which will actually provide a short baseline. So what the power of DHT is obviously that we have these telescopes spread across the globe, which provide very long baselines, which means very high resolving power. But different baseline length and different orientation actually allow to probe different portions of the source. And for example, having a short baseline means that you can recover larger scale of the source. And for example, in the case of M87, we are really happy that we managed to recover the structure of the ring very close to the event horizon. But we know that M87 has this spectacular jet that propagates outward. And if you have some shorter baselines, like 100 kilometers, for example, like in the case of Arizona, then you can recover some intermediate structure and see where the jet is launched from horizon scales. And we will be adding a telescope, actually an array of telescope like ALMA in the Northern Hemisphere, in France, the NOIMA array, which will provide another very sensitive anchor in the Northern Hemisphere. And we will be adding step-by-step more telescopes. We will love, and we are actually planning on working on adding a telescope in Africa, which now is the continent without a telescope. And that would be fantastic because it will provide mutual visibility with the European telescope. So for now, we have only IRAM, which is very important because it gives you east-west baselines, and so very high resolving power, but it's only one, and it has very few hours of visibility with ALMA and the other telescopes, especially Hawaii. So having a telescope in the south at the same meridian would be very, very, very useful. And the plan is to put it in Namibia, which will be, is more or less, I think, the same parallel as ALMA. So it will provide a very nice east-west baseline as well. So we are working in adding more and more telescope, which should provide more and more a better fidelity of the images that will be getting in the next few years.
Thank you, Ciriaco.
I would like to also, can I finish the complementation?
Of course, of course.
We're adding on bits and pieces, because I think all of us are doing a little bits and pieces. And I think we're really, that's what people said last year, we're just starting to explore this. So yes, we're adding more telescopes around the world. That's so necessary. And we're also adding better hardware. We're adding better software. At ALMA, we're also planning to offer new modes that will help study these black holes better. Like, for example, spectral lines. We'll be able to see not only flux, but get information about chemistry. We are adding more bandwidth. We're adding the ability to observe in slightly different modes that will, for example, we were supposed to be in the near future. I have a background music. Yes, for example, to observe pulsars, which is also together with the same Event Horizon Telescope. So we have really exciting years coming in black hole studies.
Okay, and what about Sagittarius A star? When or what's the challenge there we're trying to overcome?
That's the elephant in the room.
I can try to comment on that.
Well,
maybe Jeff should comment.
I can explain.
So as we discussed, as has been discussed, Sagittarius star is 1,000 times closer, and it's 1,000 times lighter, so that the ratios work out so that the image that can be made is about the same. You know, you can hold up the image and it might look like what you see on the screen now behind Hugo or Chiriaco. So that part is the same. The difference is that because it is 1,000 times less massive, light goes around the black hole, the Sagittarius A star, 1,000 times faster. And so while M87 sits still for us, we take a full night, 12 hours to make our observations. So M87 is this big, fat, heavy black hole that just kind of sits there for 12 hours and even for a week of observations. And we can add up all the data and it's a nice still picture. Sagittarius A star, because light is moving around it 1,000 times faster, well, the image can change on a time scale of minutes even, and certainly on days. And so the Event Horizon Telescope of today is not optimally designed to make that image. There's just no way around it. With the 8 telescopes that we have, it's a much harder job to make an average image. We're working very hard on trying to make that image, but it's not easy. We were rather saddened to have to cancel our campaigns in 2019 and 2020 because we would have some extra telescopes, some more data, and the possibility to make images maybe a bit faster. In the years to come, we will be adding even more telescopes, and so this job will get easier. And so the prospects are actually very good for having that image. But we don't have it. The fact that we don't have it today for you tells you that it's just a hard job. But we'll get there, and it's coming, believe me.
Excellent, excellent. We're very, very looking forward for that. I have a question from Nicolas Luco. He's a journalist here in Chile. I'm going to read it because it's a quite long one. The year ago discovery was a milestone for astronomy. It opened the way for new research so as to explain the universe. Is the jet photograph and its perpendicular light another milestone which opened new questions? Which are the main questions that will be opened from that? I don't know who wants to answer that.
Can you bring up the 3C279 image? Nico? You know, all the cartoons that you see of accretion disks and jets, all the artist conceptions, all the cartoons, yeah, any of those will do. You know, they all show the accretion disk in one plane and a jet coming out at exactly right angles. And nature is very clever and can do things that aren't really immediately obvious to us, and you see that right here. The main blob that's got the black hole and the accretion disk is not at a right angle to what is clearly a jet component moving down through the jet. I'm sure that as we study this, we will come up with some understandings of how this can happen. But this is just yet another example about how nature makes things, wherever you look, nature makes things interesting. If you look at all the planets in the solar system, and if you had never studied them, you might assume they're all spinning with their axes all pointed in the same direction. But in our own solar system, they're all pointed in rather different directions. And to this day, we don't really know why. In fact, one of them, Uranus, is spinning with an axis that is in the plane pointed at the sun. So there are reasons for these things. And in the case of the planets, we can go there and we can study them in detail. In the case of 3C279, well, it's 5 billion light years away. So all we can do is take pictures from here. But there are many other quasars, and we can now study more of them and get into the details. And so this whole process will teach us answers to these questions.
Excellent. Thank you very much, Jeff. I'm
You
having
also,
kind of,
I don't know if Chiriaco wanted to add more. I saw him moving, but before that, I thought earlier regarding this image, you were showing the time lapse, because I think this is another nice result related to 3C79, that they actually managed to find it. So in a daily base, sort of changes that show how they're not only detecting the jet and the accretion disk, but they actually see things moving on a time scale it's measurable, you know, and within just a few days. Yeah, here it is, exactly. You see variations in the accretion disk, as if like material was kind of flopping around, I guess, and the jet formation, sort of, you see here already the component is moving downwards along the jet. So you see, I see astronomy in real time, which I think is another amazing thing to add to this result, on top of what Jeff just said.
Yeah, and the scale there is light years now. We're looking, because it's much further away, this is a much larger region of space, and yet we can still see motion on the scale of light years. The nearest star to us is Alpha Centauri, and it's some 4 light years away. You could imagine how excited we could be if we saw Alpha Centauri moving as fast as this jet blob is moving. It's not, though.
And
Yes,
the other cool, surprising, sorry.
I'm sorry, go ahead.
Go ahead, Chicago. You go.
Well, I was about to say that I can add an additional point about the future results that we can get from this kind of object like 26279. One is what is shown in this nice image, the time domain evolution. So how the source moves over time, that we can track in a few days of observations. And then there is another possible image that will come at some point, which will illustrate the polarization of light coming from the black hole, because you know, light, because of interaction with magnetic field, this interaction will imprint a specific polarization signature on the light. So we will be able to reconstruct the magnetic field around the black hole along the jet, and we can also track as this changes over time. And this is part of the main question that was referring at the beginning. What is launching this? Which is the formation mechanism of this jet? And we have models that have been around since the 70s, which indicate that magnetic field lines can either be frozen in the accretion flow and pass through the event horizon. And in that case, the black hole will be anchoring the magnetic field, and it will be the extraction of the rotational energy from the black hole, which will be powering and launching this powerful jet. Or in alternative is the magnetic field, which is anchored to the accretion flow. That will be the source of energy to power these astrophysical jets. So we have more to explore, looking at different properties of light.
Yeah, I think another thing cool is that with these dynamics, with this movement, there's also some movement also in the core. And the other thing was it's still not totally clear what's the center of the core, and that's also in discussion in the paper. That normally we would go and mark the flag on the brightest spot, and actually in this system is so complex that not even that is clear. So we're really seeing something new and groundbreaking as well.
Okay, thank you. Oh, sorry, I had to leave a little for a couple of seconds. To put the shot, yeah, okay. So we're getting to the end here, but I don't want to finish this without asking you guys if you want to give us some closing thoughts about what all this means, and if you can maybe try to get this back to the present times where we are all working from home and collaborating. I know you all are in different cities, most of you. Can you, Jeff, where are you now?
I'm working from home in Massachusetts.
Massachusetts. And Chiriaco?
I'm at home in Utrecht in the Netherlands.
In the Netherlands. Well, Violet, Hugo, and Alejandro are in Santiago at home also. We're all locked down here still, no?
Yes.
Are you locked down or not? Because not all Santiago is locked down. So I don't know if all of you are locked down or not.
In my case, yes, I'm locked down.
Yeah.
Yeah, I am as well.
I don't have any chopper. I don't have to escape.
Violet, you're muted.
Yeah, hi, you can read my lips, anybody? Yeah, we're also locked down here. We're in Las Condes and we can't even get out of the apartment.
Okay,
little
so
while.
if somebody wants to give us some thoughts about, I really found this really enjoying, not the lockdown, but the fact that collaboration of all sorts is happening still when people are being locked down. And this is a situation we, of course, never wanted to have, but we're still being able to talk, to do this kind of event. And I think EHT has a lot of lessons learned about working from different cities, collaborating, and making people do things together from different parts of the world are using this kind of technology. So I don't know if somebody wants to take the lead on this, and of course everybody is invited to give some thoughts about it.
In a way, we are experts of working from home, because if you look at EHT, we have everyday telecoms involving people in US, like in Massachusetts, but then you have people in Arizona, people in Hawaii, then you have people in Japan, in Taiwan, and then we have us Europeans. And it's always a pain in the to organize all these telecoms, but we've been working like this for many years now. So in a way, we are we're kind of trained for this telework, as it's called in some places, or videocom work.
Yeah, I think that is true also for, it's true, definitely true for the EHT, is also true for people at Alma independently. We've been doing this, you know, we are from an international organization, people from Japan, like you're saying, from Europe, from Chile, from North America, always trying to find the right time zone. Always, we're used to working like this. I completely second his spirit, and I think it's really nice also to be able to see people during this difficult time and connect and, you know, think about astronomy and continue to dream despite day-to-day sort of worries.
I think it's a great time to be alive. You know, I think back to the Dark Ages, and we would have been hovering with a candle and playing with pieces of string for entertainment. So we're really, all things considered, we're in great shape.
And it's celebration time, so be happy.
I want that backdrop. Where did you find it? It's great.
This was made by one of our PhD students in Radboud and Nijmegen.
Oh, nice. Very nice.
Raquel.
I will share afterwards.
Sure.
Okay. So thank you everybody for joining us today. I think we can close with this now. And thank you, Alejandro. Thank you, Chiriaco. Thank you, Violet, Hugo, and Jeff. And of course, thank you for the ones who couldn't make it here today, but I hope they are all well, like Ruben, like Aki, like Venki, like everybody. And of course, we're meeting in a couple of hours for the Spanish version of this celebration later in 2 more hours. And just the time for lunch here in Santiago. And see you later. So Chiriaco, Alejandro, Violet, and Hugo. Jeff, if you want to join, of course you're welcome, but I don't know if the Spanish is gonna be
I think I'll watch.
I'll try to try to join. I don't promise.
Oh, Spanish. Okay,
My
we'll do
Spanish.
it. We'll do.
I'm rusted nowadays.
It's a good, it's a
Okay.
good practice. Thank you very much for organizing, Nico.
Yes,
And
thank you, Nico.
Oh,
Thank you,
bye
Nico.
to everyone.
Bye.
Have a nice
Bye.
lockdown time and take it.
Talk to you
Stay at
soon.
home.
Bye.
Stay safe.
Stay healthy. Ciao.
Ciao.
Bye.